Welcome to this explainer. Today, we're skipping right past the outer casing and diving headfirst into the actual engine room of high-performance liquid chromatography, or, as we all know it, HPLC. Whether we're talking about testing the purity of life-saving medicines or just making sure our drinking water is free of trace contaminants, HPLC separates complex chemical mixtures with, honestly, mind-blowing precision. But let's actually break down the exact piece of hardware where that magic happens. So, what exactly lies inside the stainless steel heart of an HPLC machine? If you look at a full system, it's packed with all sorts of impressive bells and whistles. You've got solvent reservoirs, degassing systems, massive high-pressure pumps, and ultra-sensitive detectors. But you can really think of all those parts as just the chassis, the fuel lines, and the dashboard of a sports car. The actual engine, the thing doing the heavy lifting, that's the column. It's the absolute core of the machine, where the stationary phase interacts with the mobile phase to physically pull apart the compounds we want to analyze. Now, at its core, an HPLC column is remarkably unassuming from the outside. Seriously, it's just a straight, calibrated tube. Typically, it's machined out of stainless steel because, well, it has to withstand immense pressure. Sometimes, depending on the chemical compatibility you need, the inside might be coated with an inert material like glass or even the specialized polymer called PEEK. Inside this tube is your stationary phase. That's the packing material that actually does all the separating. Oh, and a totally critical design rule here: dead volumes. Basically, any empty spaces where fluid could just sit and mix uselessly, those have to be kept as absolutely small as possible to maintain a crisp, clean separation. When you pull apart something like a Zorbax HPLC assembly, the science suddenly shifts from this abstract concept into heavy-duty mechanics. You aren't just looking at a theoretical tube anymore. You're seeing the main cartridge column right in the center, flanked by these incredibly precise machined end fittings and specialized gaskets. It's literally a beautifully engineered piece of analytical plumbing. And it's designed to operate flawlessly under extreme, high-pressure conditions without leaking a single drop. To really grasp how this works, we need to understand the macro dimensions of standard columns. We're not talking about massive equipment here. A standard analytical column generally runs anywhere between 3 and 25 centimeters in length, so think roughly the size of a pen, maybe up to a standard desk ruler. The internal diameter is incredibly tight, just 0.5 to 5 millimeters. And because of these strict physical constraints and that densely packed stationary phase inside, the flow of the mobile phase into the column can't be some rushing river. It literally must not exceed a few milliliters per minute. But think about this practical engineering problem for a second. If you have high-pressure liquid pumping through a tube filled with microscopic particles like silica gel, how do you keep those particles from just blowing right out the other end and totally destroying your detector? Well, the answer is elegantly simple. That stationary phase is securely trapped inside our high-performance engine by a single porous disc located at each extremity of the tube. These discs act just like retaining walls. They let the liquid mobile phase flow right through smoothly, but keep the separating material locked firmly in place. So what happens if we shrink that racetrack down even further? Enter the microcolumn revolution. The shift in scale here is wild. Some manufacturers have engineered these tiny columns with an internal diameter of just 0.3 millimeters and a total length of about 5 centimeters. And the flow rates. We go from a few milliliters per minute in standard columns all the way down to a few microliters per minute. Shrinking the hardware down like this completely changes the dynamics of the entire chemical separation. I mean, think about the sheer efficiency we're talking about. Pushing compounds all the way through a microcolumn to get complete elution requires only a few drops of mobile phase. A few drops. It's mind-blowing. But of course, you can't just plug one of these microscopic columns into a standard machine and call it a day. The entire system is so tiny that the pumps delivering the solvent and the specific nature of the stationary phase have to be completely adapted to handle those ultra-low volumes. So why go through all the trouble of engineering these tiny systems? Well, analytical chemists absolutely love them for a few key reasons. First off, they substantially reduce the amount of mobile phase used, which saves money and massively cuts down on chemical waste. Second, shrinking the hardware actually amplifies the separation power. It improves resolution by diminishing the diffusion of the sample inside the column. Less room to spread out means sharper peaks. And finally, because those solvent volumes are so incredibly small, these columns are practically custom-made for being hooked directly into a mass spectrometer, a powerful setup known as HPLC-MS. Now, whether you're running a standard column or a micro column, these pieces of equipment are highly engineered and, let's be real, very expensive. Which brings us to a super important question.
how do we protect this analytical engine? Just like a high-performance sports car needs clean fuel and a top-tier oil filter to prevent a catastrophic breakdown, our HPLC column needs a robust line of defense against contaminants. Because if you pump dirty samples through it, it's going to clog, the pressure will spike, and that expensive column is completely ruined.
This is where we shift our focus to the very front end of the assembly, to a smaller cylinder known as the removable pre-column or guard cartridge. Guys, this is your instrument's life insurance policy. It sits just before the main analytical column, and its entire job is to take the hit. It prevents the clogging of the main column, which extends the lifetime and preserves the high performance of that much more expensive piece of hardware sitting right behind it. And it is tiny. At just 0.4 to 1 centimeter long, it's incredibly short. But what's really fascinating is that this little cartridge is usually filled with the exact same stationary phase as the analytical column itself. It acts as the perfect miniaturized test run for your sample. Any chemical junk that would irreversibly bind to and ruin your main column, it gets trapped in this short half-centimeter stretch instead. And since the guard column isn't expensive, you just unscrew it, toss it out, and change it out periodically. So to make sure your instrument runs smoothly for as long as possible, every single sample has to go on a protective journey. Step 1. Before the sample ever even touches the machine, it's highly recommended to physically clean the fuel. You do this by passing the sample through a microscopic filter with a porosity of less than 0.5 micrometers. Step 2, the sample enters the machine and hits our oil filter, that inexpensive 0.4 to 1 centimeter guard column we just talked about. And finally, Step 3, the perfectly clean, filtered sample safely enters the expensive analytical column to actually be separated. When you take a step back, an HPLC system is a massive, complex, and highly expensive scientific instrument. Yet its accuracy and its day-to-day lifespan are almost entirely dictated by a tiny piece of disposable hardware less than a centimeter long. Isn't it wild that in high-stakes analytical chemistry, some of our greatest scientific capabilities depend entirely on mastering the smallest, simplest parts of routine maintenance? Thanks for joining me on this deep dive into the stainless steel heart of HPLC.